arrow keys.
Okay, good.
Will be the easiest.
Another being the son of a bitch that I can be, I would be tempted to tell BDE that it's your course. Okay, that means it's all your course. You guys got to deliver the lab
Also,
And Ray and I just did it. Ray and Rich and I were talking. Since we went to this system, now I don't think we're getting much. I don't know if we get any money,
okay.
but we're guessing that every week when we do those labs the way we were doing, they were probably putting in. I would think every fall, Ray and Mitch, not combined, but each put in about 50 hours of effort.
Yeah.
Or let's say
And also
40.
Jody used to put
And Jody, 40 hours. And then we had a TA.
Yeah.
And then we had me and Gary and now me and you. So we're guessing 200 hours per fall times 20 is 4,000 hours that we put into that course.
And we are getting nothing.
I don't think we get any. We don't even get, I don't even think we get tech fees. I don't think we get fees for it.
No.
I'm really telling this. And then the other thing is, Ray and Mitch could say, well, and like their comment was, then they're losing, well, they lose they probably lose a week's worth of potential customers to pay their salaries.
Yeah.
So no,
Yeah.
but
That's also like, yeah, lost money because of
I
not
won't,
doing
I
the
won't, I
client.
won't do that unless the old wants to turn me loose.
You should, yeah.
I should bring it up to him and tell him he wants to turn me loose and then he can be the
Yeah.
peacemaker.
But now I think Zeta has given some better
Yeah. Yeah. So I'll see.
suggestions like color coded and whatnot.
Yeah, so
People can see that better. We'll see.
So we'll go. So.
All right, I'll get back to my office.
Okay, folks, welcome you to our discussion of membrane processing. Before I get into it, I just want to walk you through what's going to be happening. The rest of this week, I'll be going through homogenization, and especially if this presentation really relates to the membrane processing lab. So this is really the basis of what will eventually you'll get the practical practice with starting next Monday for some of you. And then homogenization, or if you want to think of it, particle size reduction, emulsion production, whatever way you want to look at it, that will also be one of the labs that we'll be doing starting Monday. And we'll use different types of equipment, and I'll talk about that equipment on Monday, on Friday when I talk about homogenization. The thing with the lab, remember, because again, it's not the way it used to be when we just go in. The Kumar just mentioned the pre-lab is up on the Canvas site. Everyone should take the pre-lab before the lab. There should be a video there which walks you through what will be going on in the lab. This is especially there for the people who are not coming from your group. So we're kind of showing how the data gets collected and so forth. They're probably some of you sat through my one on the water vapor transfer last in the engineering class. The one for the membranes, if I remember right, is something like 10, 15 minutes. So it'll show you what we're going to be doing in that lab. And then again, remember, 2 of the people from your group come and collect the data. The other 2, or in most cases 3 people, will just however you guys want to divvy up coming to lab and so forth. One of the things we'll try to do, because the lab's probably take in the neighborhood of an hour and a half. So we'll start at 12:50. By 2 o'clock, 2:30, certainly you should be done. And there'd be extra time there. But one of the things you might do if you want is we could walk. If you're there to do membranes, but your group had done homogenization, if you wanted, we could walk you over and show you the equipment and stuff. So you get a little bit more of a tangible experience with it. So the bread lab, basically you guys have been around ovens enough, so that one won't be anything magical. The agglomeration, again, you could go down there. And so you could see types of things. The physical setup, if it isn't real clear from the video, it will be after the fact, but it will give you some background there. So does that make sense? Okay, so when you start talking about membrane processing, what we're really talking about is filtration. And classically, and membrane technology is something that, started to find its place in the area of potential separation technologies back in the 50s into the 60s. I'll talk a little bit more about that in a moment. But historically, we've had classical filtration. We've used filters, we've used screens, we've used sieves, basically something where we had some type of semi-permeable membrane. We applied the material to it. The smaller molecules went through, or the smaller particles, I shouldn't just restrict it to molecules. Smaller elements went through depending on that pore size, the diameter of the sieve. If you think about a screen or something on your house, you could put up chicken wire, and that's a screen, and that's if you want to just screen birds out. Most of us put screens up because we don't want the littler guys in there. We don't want mosquitoes, we don't want flies, and so forth. And then we moved to membranes, and membranes really are, if you want to think of them on an industrial scale, they're massive filters. We've all had the experience when we took chemistry labs, they would decide which Wattman number you used, right? Remember that? Wattman number, this paper filter, and so forth. So basically membranes are giant filters, and we can be talking, we're going to be using roughly, I think, 1 meter of surface area for our lab, and that's nothing. Or 1 square meter, excuse me, not 1 meter length. So what is the basic general concept of membrane processing? This is a very simplistic diagram. Every one of these membrane technologies has a semi-permeable membrane associated with it. Semi-permeable meaning some things go through, some things can't go through. Under normal circumstances, if we had this semi-permeable membrane, and we put our liquid on one side, and another liquid on this side, we'll be talking liquids here and the particles in the liquids, material would flow from one side to the other. When you do classic osmosis, and we've all done, you all probably did a little osmosis the last time you washed, assuming you wash your lettuce before you make a salad. What do? You rinse it off, and sometimes it's a little flaccid, but you put it in cold water, and what happens? It gets a little more crunchy. Why? Because the lettuce, the cells are a semi-permeable membrane. You have water on the outside and water on the inside, but the inside is concentrated. It has material. So water will flow from dilute into the concentrated, trying to dilute it down. When we get into membrane technology and something called reverse osmosis, we reverse that process. Instead of going from dilute into concentrated, we're pushing it from concentrated and pushing the water out. And how are we doing this? By applying mechanical energy, by applying pressure. We push this down. There's going to be more molecules hitting the membrane from the retentate side, as it's depicted here. That is the material that is retained. You'll hear retentate and permeate. If anytime you get around membranes, retentate, the retained material, the permeate, the material going through. And so as you apply pressure, the material will flow through. And depending on the pore size, smaller or larger molecules can go through. Does that make sense? So just the classic filtration, except we're using mechanical energy to induce flow, if you want to think of it, in the opposite direction. This is a schematic of different types of membrane porosity, if you want to think of it that way. Reverse osmosis. Material is flowing across the top of the membrane. Salts, proteins, sugars, whatever, fats, all this material what we'll be doing in class, one of them will be using whole milk and skim milk. So if we were doing reverse osmosis, the milk flows across the retentate side, we apply pressure, and water flows through. So the permeate in this case is strictly water. One of the early times that people started thinking about this, I remember doing a paper back when it was either my bachelor's, I think it was in my bachelor's degree, and I stumbled on some people at Southern Cal University were trying to design membrane technology for desalinization. Could you take seawater, run it through a membrane, retain the salt, and collect the water? Technically, yes, it will work, but I think the economics were such that you have to have half the state of California, it'd have to be a big membrane probably to make enough water to make it worthwhile. Now, as we move down to ultrafiltration, and ultrafiltration will be the technology or the technique that we will be using in lab. Same material flowing across. I'll keep using milk as my example here. And the membrane is a little looser. The pores are a little bit bigger. So salts, sugars, low molecular weight compounds. One of the things you'll notice in the permeate with the skim milk or with the whole milk, it will look a little bit yellow. Why? Because riboflavin is going through the vitamin. But what are we retaining? The fats and the proteins. And we can move down to microfiltration. And microfiltration, sometimes called cold sterilization or cold pasteurization, doesn't meet the legal standard because there could be some problems here, but basically your material flows across, the pores are big enough that your casein proteins, your whey, your lactose, your water, your everything goes through, but you retain the bacterial cells. I always have to make the disclaimer, and assuming most everyone in this class is 21 or older, but when you buy your Coors beer, if you're a Coors drinker, and they talk about it being cold filtered, what they're doing is basically microfiltration to take the yeast out, to clean it up. They don't want to lose anything else, so they utilize it's cold filtration. Nanofiltration is something that is a little bit newer, not as prevalent as some of the other technologies. Where's nanofiltration? If we go back, it is good. If you dropped it into this slide, it would be between reverse osmosis and ultrafiltration. You're taking out extremely small molecules. Why is nanofiltration utilized now? Again, because you're looking at more delicate fractionization. One of the benefits of using filtration is that you don't have to heat as high. I'm not sure you could use nanofiltration to de-alcohol, collect alcohol or something like that, but it's really going into that pore size. And even within ultrafiltration, microfiltration, you can get a spectrum of pore sizes there. And we'll talk about how they delineate that later. But most of the time, people simply talk reverse osmosis, nano, ultra, or microfiltration. This is basically what's happening. If you could get in a little submarine and go down on the surface of that membrane. We have, I forgot this, a little cartoon. We have our membrane, and the liquid is flowing, it's cross flow. It's not pressed on it, it flows across, but it's under pressure because you apply back pressure. So as long as you still have flow parallel, but it's pushing down. And so because there's enough push down, oh, I see a way to get off the highway, and you scoot out through the pore. So the liquids flow across here, One of the things that happens in this area here is you get what is called fouling or polarization of the membrane. And that will build up, and that's something you guys will be measuring as you measure your products. You will notice that we get less and less permeate per unit time. Why? Because just like in chemistry, you poured it in the funnel and it went, and then drip. And then you get real tempted. I don't know if you guys did. You get real tempted to take that glass rod and try to scrape the paper so that, and then you rip it. And your TA in the class yells at you because you shouldn't have done that. After you do it once, you realize you slap your own hand to keep yourself from doing it. But what happens, you have the velocity of flow is fairly fast. And again, you'll see that with the technology when we do it in lab. We do build up this fouling. And again, the plug pours. Eventually, if you don't clean, you can wind up literally coming to a stop. Another thing that we learned the hard way in lab was certain membranes. We'll talk about what they're made of a little bit later. But one year we went, oh, we got some grape juice left over up in McNeil, and we're not going to drink any of this or eat it. And so we brought it down here and we made up a grape juice solution and we put it in the membrane and put it in. And I think in 30 minutes, we got something like 30 or 40 milliliters of liquid went through the membrane. And all we can think of was that membrane material was acid sensitive. So it puckered up and just closed up. So we couldn't get anything to go through. So again, if you guys start working with membranes, just keep in back of your mind what you're applying it for and just go, well, it should work for that because it's rated to have 10,000 molecular weight cutoff. Yeah, 10,000 molecular weight cutoff. If it's acidic, at least on the membranes we use, it swell those babies shut. And I had to take about a 2-hour cleaning cycle to try and get them back open. I think we did get it ready so we could use it again. Our worst fear was we'd have to tear it all apart and put new membranes on. Okay, so that's the basic technology. We take a membrane, it's semi-permeable. We utilize mechanical energy, pressure. It's a liquid type separation. So we apply pressure by pumping the liquid at certain velocity. The membrane is pore size is such that certain materials go through, other materials are retained. The next 4 slides will basically walk you through some of the geometry of how people have put these systems together over the years. The first 2, I'm almost tempted to take the slides out because I don't know that virtually anyone is using this configuration anymore, but I think it's appropriate that at least you have that in your back pocket. The first of these is called the tubular configuration. As you can read here, basically you have tubes of membrane that are a 1/2 inch to 1 inch in diameter. So long, basically like a garden hose, about that diameter. And these are put into a reinforced case of fiberglass. So you put them in as these tubes into, think of maybe a 6-inch either fiber or stainless steel outer housing, and you stuff all these tubes in. And then we push the liquid through the center of that membrane material. And as it goes through under pressure, the liquid flows out. And again, we think of these tubes, think of them as big straws lying on top of each other. There's space between the tubes, and the liquid flows out into that space. And the liquid that we're on the inside, the one that we are trying to retain, that is, we're trying to concentrate something of interest in there, whether we're trying to concentrate the protein, enzymes, whatever, it's flowing through. The permeate is going out into that interstitial space. At the end of this long, maybe it's 20-foot tube. At the end of this housing, you've got an outlet, out goes the permeate. The retentate comes out through the various spigots. You can bring it together. And if it's concentrated enough, you're fine. If not, if you're in a batch mode, you just push it back through again to concentrate up to the point of the concentration that you're looking for. Someone thought, we're using a lot of floor space with this tubular thing. So let's try something different. Let's sort of make it on a micro scale or size it down. So they came up with the hollow fibril or hollow fiber configuration. So instead of thinking of it as garden hoses in diameter, in which you're pumping the liquid through, think of it as a lot of little cocktail straws with the real little holes in the middle. You can get a lot more actual surface area for liquid to flow through by putting those together. The hollow fibril technology. One of the problems with the hollow fibers is, and it's same potentially with the tubular, is if you build up a little bit too much pressure inside the tube, what happens? You blow a hole. You blow a hole. Oh boy. How much money did I just have to lose because I've got to replace everything? So it's a technology that it made sense and you could get a lot of product through it in a hurry, but fibers weren't as, the sensitivity to pressure was a problem. The hollow tubes took up a lot of space for the functional amount of membrane surface. Does that make sense? Okay. Or am I boring you to tears? So that's the problem with only 4 people in the audience. I can't. And then with masks on, I can't even get twitchy face reads. So the third approach, and this is what we'll be using in class. We use what's called a plate and frame configuration. And in a plate and frame, it's set up like a plate heat exchanger. And what we have is that we will have a piece of membrane material. We will have a spacer collector, and then another piece of membrane, then another spacer, then another membrane. Think of it as a sandwich. In our case, I was just cutting membranes this morning. They're about 8 inches in diameter. So we put this sandwich together. Membrane, spacer, bup, 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 and up we go. And what we're able to do is the configuration we are able to push the liquid into the center of this, in our case, round discs. The liquid flows out, pushes through. It's under pressure. The smaller material will go through. There's a plate that'll have a little nipple on the end with a little tube, and the permeate flows out. And the retentate simply cycles back and goes through until you get it concentrated to the extent that you want it concentrated. Plate and frame, very commonly used. Not as common as what I'll show you the last approach that's used. But the nice thing with this is that people could put it on skids. You could literally put it on a semi, bring it to your plant, use the forklift, haul it in, plunk it down, pipe it up, and away you went. The most common approach today is what's known as the spiral wound type of geometry. And as it says here, this design tries to maximize surface area in a minimum amount of space. And what it consists of is layers of membrane and support material. And basically what we could do is if we were making it here, we'd put down support material, big sheet of it. It's like running a wrapping paper off the roll in the grocery store in the shop. One roll, then we layer in a layer of membrane. Then we cut them off on the ends and we roll them up. Just go, just like a sausage, roll them up. And the way that we, and I don't understand exactly how it works on the ends, and even the systems we have up in the pilot plant, we have a couple of big spiral systems up there. But you're able to pump in your liquid. It goes through, think of it, goes through the site, goes through the swirl, the spiral. As it's going through the spiral, the permeate is going through to one side of the collecting, to the support material. Retentate is staying on the membranes side, flows out, and you continue again to do it in a batch type configuration. This one's always one that you have to, I know most of you are going, what's he saying? It's a little bit hard to visualize. Hopefully we'll be able to, we used to have an old piece up in the pilot plant. I'll see if I can find it and bring it out so that during the course of the 5 labs, you can all come over and take a look at it. So then this spiral goes into a stainless steel housing. All of these will have to have some type of housing to collect things in. Okay, what are the membranes made of? And this has sort of been a progression in the ability of the material scientists. This is really the world of the material scientists to create these membranes. Initially, membranes, and we're talking 40, 50 years ago, the initial membranes were made out of cellulose acetate material. Problem with cellulose acetate is that it has some limitations as to the acidity that you can run through, acidity of the material. It has a limitation as to heat. And it didn't like something called chlorine. And why is that important? You can't, yeah. Comment from one of the people here, clean it. Yeah, you couldn't sanitize it. So they had to use enzyme type cleaners and stuff. So the technology was still being used quite a bit. There was a individual at Cornell by the name of Frank Kozakowski. And every year when you went to the American Dairy Science Association, you had a couple of Frank students there telling you how to make cheese using membranes. Because it was a way to concentrate up the product and the milk and make cheese from it. Jokingly, people said it was have membrane unit will publish was the technology used. Then people were able to utilize polysulfones, more synthetic materials. The whole key in this progression is being able to control the pore size. Consistent pore sizes. So certain materials go through, certain materials are retained. So we went from cellulose acetate to polysulfone to the polyamide materials. And this is where a lot of materials are right now, the polysulfones, polyamides. But as the technology or the chemistry abilities of the material scientists kept improving, they're actually able to lay down ceramic material with controlled pore sizes. Stainless steel, believe it or not, with pore sizes. And they're continuing to add to this. There are some real advantages to these last two, as we'll talk about in a moment. But they're not cheap.
The ceramic ones just chip really easily.
Basically what the ceramic ones are, this question here, when they chip, they're laid down as think of it as a big tube with little holes through it. And so it's really a wood chip, but it's pretty rugged stuff. And you got to be careful with it. It's not a little thin tube. The piece I had was maybe an inch in diameter. And so it had holes through it, channels like a straw size or a little bit. And so you'd pump your liquid through the straw, and then the permeate would work its way out through the ceramic to the outer housing where it'd be collected. But again, it's not a cheap technology. So it's got, I don't even know where the specialty applications are. Basically the material you use, you have some cleaning issues. Composition of the membrane, cellulose acetated, as I said, didn't like below about pH 3 to 4 and didn't like above pH about 10. So on the 10 side, you're looking at caustic cleaners. Oh, it didn't like chlorine, so the chemicals being used and so forth. One mistake someone made one time is they were doing some apple juice concentration, and for some reason it plugged, and they got the wise idea, because of it being all cellulose material, let's put a cellulase in there. No, you don't put a cellulase enzyme in with a cellulose acetate membrane. Not only did it eat the cellulose, it ate the membrane. So again, the conditions, this temperature range, as you go from the cellulose acetate, working your way down that list, you're able to go to more severe chemicals, higher temperature conditions in order to get the effective cleaning. Also, depending on the product, you might want to use different temperatures to do your separations. What we'll be doing is running at 120 degrees Fahrenheit, roughly 50 degrees Celsius, because the higher the temperature, the lower the viscosity, as you're all aware. So the easier the flow and the quicker the concentration, right? So why not run it at 140, 150?
Does that increase the pore size?
Well, that's a possibility, but more importantly, what happens to proteins as you pump the temperature? You denature the proteins. So that 120 we use for milk is sort of the best of both worlds. As high as we get relatively lower viscosity without denaturing the proteins. So that's something to think about. If you're looking at something that where temperature doesn't really make any difference, you could pump it up to 160, 170, because you get less viscosity, so better flow and thus faster separation taking place. Back flushing. Something plugs up. You get something plugged up. What do you do sometimes? A little tube, little something in the kitchen. Take it and you try and blow it out, right? And you don't do that with cellulose acetate, polysulfone, those membranes, because if you try to blow it out from the backside to back flush, push liquid through it, you blow holes in it. The ceramic, the stainless steel do allow for back flushing because they're rugged enough that they can take it. Again, the cross flow that's going on. One of the things that some people will say is that as you build up this boundary layer, that is almost like a secondary separation membrane, because as that material deposits, it has its own structure and therefore able to alter porosity as well. Something called diafiltration. Basically, when would you use diafiltration? I've concentrated, and the upper limit, especially with things like milk, is once you get in the range of about 25 to 30% total solids. Your viscosity is getting too high, your flow rates are too slow, and that's just a problem you've got to deal with. But you're going, shoot, I'm not getting out all the stuff I want to get out. So this may sound counterintuitive, but what do? If again, the economics work out, what you do is you take your 25% concentrate and you dilute it back down to, let's say, 12%, and you run it through again. And as you run it through the system, the water you put in goes out, but it also carries out more of the material that you want to get rid of. So if you're really trying to clean something up, a protein solution, for instance, and this type of technology is utilized in the medical profession too. There are little mini UF type units used in some hospitals in order to prep samples for analysis. So diafiltration is basically, think of it as a second separation of the same material, but the step being that going from step 1 to 2, you diluted it down in order to make flow greater through the membrane, but yet you're concentrating a material of interest. Might be something you'd utilize if you're really interested in isolating something like a specific enzyme or so forth. But again, on an industrial scale, not quite as common. Electrodialysis, again, not utilized a lot, but it is a technology that some people use. And again, it is predicated on membranes with certain pore sizes, but also utilizing the charge on the particular molecules. So you basically have an anode, positive, a cathode. You have your membranes in the system. You pump your solution through. Your negative charged particles are pulled towards the positive. The negative go the other way, or the positive go the other way. And as you circle through with time, you're able to concentrate or separate based on charge. So if you're trying to desalt, not on a large scale, but some type of, again, enzymes and so forth might be a good application for this. Some additional terms that you'll hear people talk about when you're dealing with membrane technology. The membrane is said to be asymmetric. That is, if you took it and looked at it under a microscope, it is not the same pore size from top to bottom. It will be a little bit asymmetric. So maybe you have a smaller pore at the top, a larger at the bottom. So once it gets in, it flows through quicker and so forth. Composite membranes, just as you would guess it is, maybe you take a polysulfone membrane, which has certain characteristics, and you layer a polyamide membrane with it, make a membrane sandwich because of the characteristics that they have for a particular application. Concentration factor, and we'll look at a very simplistic, it's a very simplistic calculation, but the concentration factor is simply, I start out with X amount of material, and how concentrated do I get it in my final retentate? So if I start out with 300 gallons and wind up with 100 gallons of retentate, and we assume that our material of interest is in the retentate, what, threefold concentration? We have concentrated it threefold. And that's one of the calculations that you guys will be making in the laboratory. I mentioned concentration polarization before, or what is simply referred to as fouling. Fouling is, again, back to our chemistry lab days, when we start to get crud material on the surface of the membrane. it slows down the rate of flux. Flux, the units of flux would be liters per minute per square meter of membrane or something of that amount. So it's the amount of liquid in a given time going through a certain amount of membrane surface. And obviously, as a processor, you want to keep that flux as high as you can. Because what is time? It's money. We want to get it through as much material as we can. Molecular weight cutoff. This is something that you will come across when you are buying membranes. They'll say, well, what molecular weight cutoff do you want? Basically, they rate the membranes utilizing what are called limit dextrins. So you cut starch into certain molecular weight sizes. And if you get let's say a 10 kilodalton membrane, it means that the any dextrins less than 10 will go through, the bigger ones are retained. So your cutoff is at 10 kilodaltons, 30 kilodaltons, whatever. Now, that sounds, oh, that's easy. We just pick it off the shelf. But the other thing you have to keep in mind is all of the materials that you may be concentrating behave a little bit different chemically. But using this molecular weight cutoff definition or defining process, you're able to at least get a good ballpark as to where to start for the membrane that might be of interest for your technology, for your use. If you're trying to separate certain proteins, and you say, well, that protein's got it's a 15,000 kilodalton size protein. Well, maybe 15 is going to work, and maybe you need a little bigger, and maybe you need a little smaller, because again, the configuration of that protein may come into play, but it at least gives you a way to compare membranes from different types of companies. Osmotic pressure, again, osmotic pressure is what we're overcoming, because the water is going to want to flow from the concentrate or from the dilute to the concentrated, but we want it to flow in the other direction. And as you build up more and more osmotic pressure in the system, and this is true not only of reverse osmosis, but ultrafiltration, nanofiltration, and so forth, as there's more back pressure from the liquid, you have to put more in from the other side. And there is a upper limit as to how much pressure you can apply. It's called kaboom, blow the system up. Same thing applies to plate heat exchangers. I watched somebody blow one up one time. Ran stuff through it they shouldn't, plugged up, and what happens on plate heat exchangers, they have little black snakes. The membranes, the gaskets start to get squeezed out and see little black snakies coming out of your system. But you don't want to, see, one of the things that we'll deal with is we play with the pressures, back pressure, forward pressures, and so forth. Turbulence. Turbulence is your friend. You would like turbulent flow going across that membrane, because that not only gets more material in contact, but it also helps, in a sense, to clean as you go with your current material that's in there. Just a couple little terms that you'll hear, some little calculations. One of these is the retention factor. That is how much of the material in question is being retained in your flow, in your material that's flowing in. So the retention factor is the concentration in the feed stream minus the concentration in the permeate stream divided by the concentration in the feed, or if you want to think of it, the retentate. And you would like this number to be very high if the material of interest is in your feed stream, because you're trying to, let's say, remove water, sugars, salts, and concentrate up enzymes. or one place that you'll see this technology has been used, it's a front end step in the production of whey protein isolates and whey protein concentrates. Membrane technology was really one of the technologies that allowed that industry to boom, because you could concentrate using membranes, get rid of, take that whey, you were able to get rid of a lot of the lactose. You were able to get rid of the minerals and concentrate the protein. You're able to possibly, get up to, get the percentages such with the membranes that when you take the material, you get it to a third protein and then go to a spray dryer, you wind up with roughly 36% whey protein concentrate. So it'd be 36% protein. If you want to go higher, utilizing membranes, you could utilize diafiltration, again, flushing out and just keep concentrating the protein. But you reach an upper limit as far as the solids that you can get in there, plus the amount of time you want to be running water through, cleaning things out. So the technology that Davisco utilized early on was basically they were using industrial scale ion exchange. Put the whey in, proteins that stick to the column, all the crap, the lactose and other things would go out, change the conditions, out popped a stream of protein, dry it, and you just say the rest is history, the rest is a bunch of money that was made. Got to tell this story because they used to sit in the front row here. Two of the Davis brothers, Mitch and Marty Davis, are graduates of this department in food science back in the early 80s. At that time, they came from, their dad was Mark Davis, and Stanley, the grandpa, owned LeSueur Cheese and another company, a butter factory in St. Peter. They were doing very well, and Mark Davis had the vision that maybe whey protein, how many letters in whey? It's a 4-letter word. When I came to Minnesota roughly 40 years ago, it's a dirty 4-letter word. What do we do with this crap? It was it's in the cheese industry. It's crap. That's why little cheese plants sit on the top of hills with a stream down below, so you can run the whey down. You can't get away with that today. But that was what was being done, trying to get rid of. And he had the vision. He got the patents from Wales, and they went to industrial scale separation. So rejection factor is really how much is being rejected by the membrane, that is staying in your feed stream. The one probably of most interest is the concentration factor, your initial volume and your final volume. In our case, we'll be doing initial weight and final weight in lab. You start out with 900 liters. We wind up with 300 liters. We've concentrated threefold. If we work on the assumption the material of interest stayed in the retentate, we now have concentrated our protein, our fat, our enzyme threefold. What is the upper limit of concentration? Nobody's doing concentrated milk this year, but the evaporated or the non-fat people may want to think of this one. Membrane technology is great up to about 30% solids. Then you get pretty concentrated. The benefit of doing the membrane is that you don't have a phase change, therefore less energy. So a lot of people would say up to roughly 30 to concentrate by membranes, 30 to 60, 65 to concentrate with an evaporator that is boiling the water off. And then that gets ineffective. Then you have to go to the spray dryer. So if you think 30, 60, and then eventually 95 plus, it's just one way to think about where this might fit into just general everyday process technology. Just wanted to mention a couple references. This is a website for the CDR, the Center for Dairy Research at the University of Wisconsin in Madison. And they have a lot of good items that you can pick up off their website if you're looking for just quick primers on different things. The other place that I do need to make sure, because I'm somehow slipped over the slides that I used today were from the University of Guelph in Canada. University of Guelph has a fair concentration of dairy processing people, and they're a great place. At least I haven't been there in a few years, but they had a lot of nice little PowerPoint sets like this, so that if you're looking for a quick primer or quick, how does this work? I think they had ones on pasteurization and separations and other things. But if you're looking in the US, the CDR is where it's at, to the extent that they just got money from the state and the industry to put a $45 million addition onto Babcock Hall, which is the food science department, but it's where the Center for Dairy Research is located. So with that, that's the wonderful world of membranes. I'll see 2 of you next Monday doing membranes, and we'll go from there. So again, if you have questions on your projects, feel free to ask. I know one of the groups got a lot of information the last time I lectured, because we got talking about the ice cream project. And I know 2 of my TAs for 1011 know that I'm open territory up in class when in between lab sections and so forth to go through things. So my plan is to get through your what you turned in, flow diagram. Some people had flow plans and stuff, to get through that, have it available, and we'll give it back to you in lab on Monday. So I'll find who's ever got, wherever the ice cream people are, we'll get it to who's ever TAing that session. So with that, I know I ran a little bit long, but again, if you have questions, take care. And for those of you that aren't graduating, we are working on the schedule for fall. I think registration starts right after break, so things are being worked on.
So